Hey, welcome back. Do some videos here for the homework for 10.5, continuing 10.5. I had finished up number 13 and I was moving on to 15. So let's take a look at this. All right. Find the vector equation for the line segment connecting the, from the point 2, -1, 4 to the point 4, 6, 1. So we want the vector equation that's going to connect this point to this point. And the important thing is that we want the segment, not the complete line itself. So if I were to, sketch this thing, oops, 2, 1, 2, -1, 4, point something like that, then maybe like 4, 6 would be maybe down here, and then 1. So we've got these 2 points. I'll call it, point A and point B. So we want to look at the line segment that connects these two. We do not want to continue and extend that line forever. All that means that we're going to need to restrict what t is. All right, so we're not going to let t be all real numbers. If we do that, it'll draw the whole line. And so what we do is we need to find a point on the line and a direction. Well, we have 2 points to choose from. And so if you're going to use the method that I show in class, what you do is you always pick the point you're going to start from as your R0. So we're going to choose R0, that vector, to be the starting point converted to a vector. And that's going to, I'll try and draw here what's happening. From the origin to that point right there, that's R0. And now what I need is a direction vector. And the direction vector I use is the vector that connects point A to point B, right? This is point A. This is point B. And that vector is going to be my direction vector V. So V is the vector connecting these 2 points, right? This point to this point. So I'm going to go 4, take away 2, that's 2. I'm going to go 6, take away -1, that's 7. And I'm going to go 1, take away 4, that's -3. So that's my direction vector V. And so I come up with my formula. My formula will be R of t equals R0 plus t times v, which is 2, 7, -3. Now, again, the key to this is that if t is all real numbers, then it's going to draw the entire line, not just the segment. But if you do it the way I showed you here, you start at this point, you're going to this point, so you convert this to the vector, you use the vector from A to B as your v, then you will always just restrict t between 0 and 1. Now, you could also write that t is an element of the closed interval 0, 1. Either way. And so what happens is if t is 0, right, then this is all gone, and you're just pointed out towards this point right here, right? You're the red vector, which points you here. So you're at the start. And then if t is 1, let's just say t is 1, which would be the extreme other end, then you add these two. This will be 1 times this, which is just this vector. You add these two together. 2 plus 2 is 4, and that would give you this. -1 plus 7 is 6, that would give you this. And 4 take away 3 would be 1, and you'd be here. So then, at t is equal to 1, you're actually from the origin to this point. And so you take some t that's in the middle, like let's say you take t is 1/2. So what you're going to do is you're going to take this vector, you're going to add half of this vector. So this vector goes from here to here. Then you're going to add to that half of the green one, which will take you halfway down the green one. And so the resultant vector, right, starts at the origin, goes here, then goes halfway, is from the origin to this point on the line. Ooh, line segment right there. So you can kind of see that, you know, if t was 0, you're here. If t is 1, you're here. If t is a half, you're here. So if t is a quarter, you're going to be here. If t is 3/4, you're going to be here. And if t is everything between 0 and 1, it's going to draw the entire segment, but nothing further. All right, that's 15. Oh, you know what? I could put these together. I never did that. You could get a final answer here. R of t equals, just put these two together. So 2 plus 2t, negative 1 plus 7t, and 4 minus 3t. And of course, t is between 0 and 1. What are we doing now? 17? Determine whether the lines L1 and L2 are parallel, skew, or intersecting. So we have two lines. L1 is given by the parametric equations. X equals 3 plus 2t. Y is equal to 4 minus t. Z is equal to 1 plus 3t. L2 is X is 1 plus 4s. Y equals 3 minus 2s. And Z is 4 plus 5s. So they're using the variable s in the second line as opposed to t in the first line. So that's just because you want to be able to draw this one, letting t be all real numbers. That'll draw the entire line. And then this one, you could use t again, but we're going to use s because there's nothing that says you have to draw both these lines at the same time. So if I plug in t as 1 here, right, and just draw whatever vector that draws or point in three-dimensional space, then there's nothing that says that I have to draw this point at 1 also. S is 1. I don't have to do that at the exact same time. So these two lines aren't connected by the same variable of t. So that's why we use a different variable, s. All right, so are they parallel, skew, or intersecting? All right, so are they parallel, skew, or intersecting? So here's what they want to know. Visually, this is what we're looking at. You've got two lines in three-dimensional space here. I'm trying to figure out if these lines are parallel, which means they would point in the same direction. Are they skew, which means that they aren't parallel and they don't hit each other? Or are they intersecting? So do they actually hit each other, right? Cross somewhere. All right, so what should we check first? Why don't we check for the parallel? So to be parallel means that these two lines have to point in the same direction. So why don't I try and find the direction vectors for each of these lines? Remember that each of these lines, you can find the direction v. I'll call it v1, and for this one I can find v2, so which way they're pointing. And from what we've done in the past, we know that the direction vector comes from the coefficients of the variable in the parametric equation. So the 2 here, there's a -1, and then in front of this t we've got a +3. So what I can say is that the direction of line 1 is the vector 2, -1, 3. I can do the same thing for L2. I can find its direction looking at the coefficient of the variable, so 4, -2, and 5. So the direction of the second line is 4, -2, and 5. So the question is, are these parallel? So we go back to, how do you determine if two vectors are parallel? Well, we want to see, is V1 some multiple of V2, right? So is there a number that I can multiply to get from this vector to this vector? So can I scale this vector in a way that it creates this? Well, the only way I'm going to be able to do that is if I can get the 2 to become a 4. So how would I make the 2 a 4? I would actually have to double, right? So also, I could have written this instead. V2 is some multiple of V1. It doesn't matter. Either one of these, I just need to show either one of these is true. So I notice that if I take V1 and I multiply it by 2, I'm going to get a 4 here. So I'm kind of saying this. The question is V2, is it 2 times V1? Well, the first component's okay, right? If I take 2 times V1, I get 2, and then, I'm sorry, I get 4. But then the next component, I multiply here, I get -2, and then when I multiply that by 2, I get 6. And you can see here that if I do this, I do not get V2. Yeah, the first component's the same, but these two are, well, this component, sorry, is also the same. That works. But the third component doesn't match. And so there's no way I'm ever going to be able to scale V1 by a number and get V2. It's just not going to happen. So they are not parallel. Let me see. Are they skew? Well, that's actually very difficult to show because what we need to do is show that the vectors don't hit each other. Like there's never a point that they hit together. So what I'm going to do to determine if they're skew is I'm going to ask myself, are they intersecting? So do these actually share a point? Do they actually hit at some point? So remember that for different values of t, right, I draw different points. They're really vectors, but they correspond to points on the line. So for different values of t, I draw all these different points. And for different values of s, I draw all those points on the second line. So the question for the intersecting is this. Does there exist a t and an s such that the first line, L1 at t, is the same as L2 at s. So is there some point in time, t, right, or some value of t, that when I plug it into L1, it matches with L2 for some value of s? Now, I think I'm going to write this a different way. Okay? So what I'm going to do is I'm going to rewrite L1 in a vector form, a vector function. So I'm going to call R1 of t, which is L1, so this is R1, is going to be this written in its vector form. So 3 plus 2t, 4 minus t, 1 plus 3t. And then I'm going to write the vector form of the second line, which I'll call R2 of not t, of s, equals 1 plus 4s, 3 minus 2s, and then 4 plus 5s. So that question I was just asking is saying this: is there some value of t that when I plug it in here, I can get it to match with this vector for some value of s? So I'm trying to find a t and an s that I plug into both of these and I get these things to match. Well, let's think about what that means, all right? I'm going to need these to match, I'm going to need these to match, and I'm going to need these to match. So that means I have 3 different equations that have to be true. I have to have 3 plus 2t must equal 1 plus 4s. I need that to be true. I need 4 minus t to be equal to 3 minus 2s. And lastly, I need 1 plus 3t to be equal to 4 plus 5s. And so what I have is a system of equations here. Yeah, that's good enough. Well, maybe not. That's not a very good brace. Okay, so I have a system of equations. And I have 3 equations, but I only have 2 unknown variables. So I should be able to get this with relative ease. What I will do is I will rewrite just the first 2 equations. I'm going to bring all my t's and s's to one side and all numbers to the other side. So 2t I'm going to leave here. I'm going to bring the 4s to this side, so minus 4s equals, and then I had a 1 here, a 3 here, I'm going to subtract, so I'm going to get negative 2 here. So that's the first equation rewritten. Second equation is negative t, and then I'm going to bring this over, the negative 2s becomes plus 2s, and then I have a 3 over here, I'm going to subtract 4, I get negative 1. So that's the first thing I have to be true, right? This has to be true and this has to be true, which means these 2 have to be true. I'm going to worry about this one in a second. So now for this simple 2 equations, 2 unknowns, I can use elimination, I can use substitution, depending on what you've done in the past. I'm just going to do elimination, and what I'm going to do elimination is I'm going to try and kill off the t's. So I'm going to multiply this equation by 2 and then rewrite the system. So I have 2t minus 4s equals negative 2, and then here I get negative 2t, and then 4s equals positive 2. And this is strange. When I add down, I get 0 equals 0. Well, what does that mean? What does that mean? 0 equals 0. If you recall back from solving systems of equations back in college algebra, when you get something like this, that actually means that there's an infinite number of solutions. If I plug in a t for this, there's going to be an s that works, and the same t and the same s will work here. So there's an infinite number of pairs that are going to work here. So I don't really have a lot of information from this. So what I'm going to do now is I'm going to move on to this right here and work with, let's say, the second and third equation. And let's try and rewrite this again. You know what? I don't need this anymore. So let's take this equation, the second one, which we already had simplified over there, brought everything over. Negative t plus 2s equals negative 1. And then I'm going to do the same thing for this one. So 3t, and then I'm going to bring over the 5s, so minus 5s equals, and then I'm going to bring the 1 over here, so 3. And let me do the same thing. I'm going to try and solve that. So I'm going to eliminate the t's again. So I'm going to have to multiply the top one by 3. Top equation. I get a new system, negative 3t. I get positive 6s equals, let's see, negative 3. And then over here, nothing changed. Equals 3. So now we add straight down. We get 0. Here we get s equals 0. Now that's some information. It's saying in order for these to be true, right? For these to be true, I need S to be 0. So if S is 0, now I go back and I can plug in for either one of these, S is 0. So let's take that first equation up there. Negative t plus 2 times 0 must equal negative 1, which means that negative t must equal negative 1, which means that t must be 1. So this is what I think is going to work. I think t is 1 and S is 0 should make these two lines intersect. However, we need to check it. Okay, so I had erased them. So let me put them back up here. Which number was this? This was 17, right? So remember, I'd said R1 of t was the vector 3 plus 2t, 4 minus t, and 1 plus 3t. And R2 of S was 1 plus 4s and 3 minus 2s and 4 plus 5s. Okay, so what I'm saying is I believe that t is equal to 1 and S is equal to 0 will work. And remember, these equations came from these last two, right? We were working with this one, and then we simplified and got to these two. So let me just check these two should work. If I let t be 1 and S be 0, what happens? So if t is 1, right here, I get 3. I'll just put it above there. I would get 3 here. If t is 1 here, I'm going to get 4. Okay. Now let's let S be 0. If S is 0 right here, I get 3. And if I let S be 0 here, I get 4. So look, they're matching. The question still remains, though, what about the first component? I know that t is 1 and S is 0 will force these two to be the same. That's the only way I can do it. Here, though, if I try t is 1 and S is 0, if t is 1, what happens here? We get 5. And if S is 0, I get 1. And these two don't match. So I went about this and I tried to find, I'm trying to recap here. I'm trying to figure out what makes these match, and these match. When I tried to figure out when these two matched, I figured there was a bunch of different values I could do. There was an infinite number of solutions. So that wasn't enough for me to nail anything down. So then I went with these two. When I went with these two, to make those match, I have to have this happen. But if that's what has to happen to make these two match, then this also needs to work for this, but it doesn't. Therefore, these two lines cannot possibly intersect. I can't find a T and an S that works for both, or works for all of these. So they don't intersect. And if they don't intersect, then it's a skew. It's a skew line. Okay. What's next? I would encourage you to try and do like number 18 on your own. 18, they turn out to be parallel. See, 19, they're also parallel. Oh, sorry, no. 19, they do intersect. 20 is skew. So maybe I should do 19. What do you think? Should I do 19? No, I'm not. What happens is that, let's say on this last problem, I think we had, what, 3 and 4 matched up in the second equations. In number 19, if you work through this and you get your S and your T, and you check these and they matched up 3 and 4, and let's just say the first one when we plugged in the two values for S and T, that these match too. Let's say this was 7 and 7. Then you would say they intersect, and you would actually say they intersect at the point 7, 3, 4. Okay, whatever these components were, that's the point that they hit each other. You would not put as your answer s is 0 and t is 1, because you would want to know where they intersect. So you would say the lines intersect at the point 734. All right. And of course, if they're parallel lines, then in that first step when we were checking the direction vectors, they would have been parallel, so they would have been scalar multiples. So like on number 18, I said are parallel. Okay, what's next? 21. All right, so here's where we start getting some good stuff. 21. All right, the instructions here are to find an equation of the plane. So I have a plane that's through the point -1, 1/2, 3. And then the normal vector is given to me as I, 4j, k. So 1, 4, 1. I'm going to go in my notes real quick and make sure I use the same formula that I used in class. So equations of planes. So this is note 10.5.14. Remembering that for a plane, the equation of a plane is given by A, x minus x naught plus B times y minus y naught plus C, z minus z naught equals 0. Where ABC, these numbers ABC, are the components of the normal vector, and x naught, y naught, z naught is a point on the plane. So what we know basically from this formula is that if someone gives us a vector that is parallel to the normal, so any normal vector to the plane, and a point on the plane, we can find the equation. And in this example, or in this problem, they give us exactly what we need. They give us a point, and they give us the normal vector. So all we have to do is plug into this. You know, this is A, this is B, this is C, this is x naught, y naught, z naught, and we just plug in. So I'm going to do that right now, and then we're going to clean it up and have a nice answer. All right, so A for us is 1, so 1, x minus -1 is plus 1. Plus, let's see, B is 4, and then y, let's see, minus 1/2, plus C, which is 1, and then z minus z naught, which is 3, equals 0. So that is the equation of the plane, but we're gonna distribute and make it look a little different. So passing things through here, distributing. There we go. And now what I'll do is I'll get all my letters, variables on one side, x plus 4y plus z equals, and then on the other side, the numbers. So I have 1, take away 2 is -1, minus 3 is -4, but then we move it to the other side, so 4. That is the equation of the plane that goes through that point and has a normal vector of 1, 4, 1. All right, let's look at number 22. That problem was about as easy as they get. Find the equation of the plane through the point. So they give you a point 2, 0, 1. And they tell you that it is perpendicular to the line x equals 3t, y equals 2 minus t, and z equals 3 plus 4t. So let me try and illustrate this. Give me just a second. I'm going to go grab something. Okay, I went to go find a plane. So here's a nice rigid plane. I'm trying to find the equation of this plane. And what I know is that it goes through that point. So remember, for a plane, we need a point and a normal vector. So I have a point, so that's good. The only thing left is to find a vector that runs out of the plane, so perpendicular to the plane. So any vector that runs perpendicular to this plane will work. And they give us that this plane needs to be perpendicular to this line. So now we've got some line that they're giving us that's sitting out there, right? And we know that our plane has to be perpendicular to this. So if we were to move this vector towards our plane, our plane would have to run in there at a 90-degree angle. So notice that the direction, right? The direction vector of this line would qualify as a normal for the plane. So all we have to do is identify what the direction of this line is. So if we look at this as a line, what is the direction vector, which we call v, of that line? So remember, all we do is we pull the coefficients off the t's. So 3, here -1, and then here 4. So I know that the direction vector of that line is the vector 3, -1, 4. And then, because my normal needs to be pointed in the same direction as that, I can just say, let's let the normal be that same vector. And of course, that'll point in the same direction. It's the same vector. Now, you could double it. You know, you could say 6, -2, 8. You could be crazy and divide by 2. You could scale it. It doesn't matter, as long as it's pointed in the same direction. So at this point, I just go straight to the formula. A, x minus x naught, plus b, y minus y naught, plus c, z minus z naught equals 0. Here's my x naught, y naught, z naught. And this direction vector is my normal vector, so that's ABC. So I'm going to get 3, and then x minus 2, minus 1, and then y minus 0, and then plus, let's see, c, which is 4, and then z minus 1, right, equals 0. And then I'll just clean it up. So distributing through here, we get 3x minus 6. Distribute -1 through here, we get -y, and then the 0 doesn't matter. And then plus 4z, and then minus 4 equals 0. And get all the variables on one side, all constants to the other side. -6, -4 is -10, take it to the other side, 10. This is the equation of the plane that passes through that point and is perpendicular to the line that was given to us. So that's number, what, 22? Okay. Number 23. Same thing. Find the equation of the plane through the point. Wow, they keep on giving us a point. This is, they're making it easy. They give us a point, what do we need? That's the only thing we need. Direction vector, right? And I need to be parallel to the plane, and then they give me a plane equation. 5x minus y minus z equals 6. Wow, okay. So they give you a point sitting out here in space. Boom, there it is, right? They give you a plane, boom, sitting right here out in space, right? That's what they give you. And you're trying to find the equation of the plane that goes through this point that's parallel to this plane. So imagine just moving this plane up, right? Don't tilt it, just bring it up, slide it over underneath, and put it where that point's on that plane now, right? Then do you agree that the normal vector on this plane, right, when we slide this up, is also the same as the normal vector on the plane we're looking for? So we actually have a point that we need to have, right, for the equation. And then we need the direction vector, but the direction vector, the normal vector for our plane, is exactly the same as the normal vector for this plane. And so all you have to do is identify what the normal vector is for this plane, and that's super easy to do. All you do is peel off the coefficients of x, y, and z. That's it. The numbers in front of x, y, and z will be the normal vector of that plane. So the normal vector of this plane is 5, -1, -1. And well, hell, we're going to use that as our normal vector also. So let me do this kind of quick. I'm going to use the formula, right? This is a, b, and c. And then this is our x naught, y naught, z naught. And I'm just going to do it all together at one time. So 5, and then x minus x naught plus b, but it's -1, and then y minus y naught, but that's +1, and then c, which is -1, and then z minus z naught, but that's z plus 1, so that's equals 0. Distributing through, 5x minus 5 minus y minus 1 minus z minus 1 equals 0. And we should get 5x minus y minus z equals, let's see, this is -6, -7, take it to the other side, so 7. This should be the equation of the plane. And what you'll recognize when you look at this is that if we go back up to this one, this was 5x minus y minus z. That was given to us in the problem. You'll notice that these two equations are very similar. Well, they should be. They should be pointing in the same direction, which they are, 5, -1, -1, right? Same direction vector. The only difference is the constant on the other side, and that's really what had the effect of moving it. And it moved it exactly so that it would pass through that point. So should we check it? Let's just check. Does this point live on that plane? Let's just plug in 1, -1, -1. So what happens if we plug in 1 here? We get 5, -1 into this, negative is plus 1, and then we plug in -1 in there, we get plus 1 again, and is that 7? Well, 5 plus 2 is 7, that's checked. So yeah, that point lives on that plane. Cool. All right, 24. So find the equation of the plane that contains, the plane contains the line, and they give it to you in parametric form. X equals 1 plus t, y equals 2 minus t, z equals, come on, where are you? 4 minus 3t. And is parallel to the plane 5x plus 2y plus z equals 1. All right. So in this problem, we're asked to find the equation of the plane that contains this line and is parallel to that plane. So let me show this to you again. So we have a line sitting out here in space. Here it is. And we have a plane, okay, that's given to us. And our plane that we're trying to find contains that line. So let's just say the line that we have, right, goes into our plane. But see, there's all sorts of planes that would contain this line. If I rotate this around, the direction of the line doesn't change. So there's an infinite number of planes that contain this line. But what we want is to find the equation of the plane that has this line in it, but runs parallel to some other plane that's given to us. So there's another plane sitting out here, and whatever direction it is, we need to kind of rotate this plane around this line to make these two parallel. I hope that makes sense. But we can get caught into, trying to understand it, visually, and that can sometimes be hard to do. Let's just get down to what it is we need for the equation of a plane. For the equation of a plane, you need two things. You need a point, you need a normal vector, right? That's what you need. All right, so let's discuss the normal vector, because this problem is very similar to the last one. We have to be parallel to a plane, right? To be parallel to this plane means that I can use the normal vector of this plane as my normal vector for the plane I'm looking for. So why don't I let my normal vector be the same as the direction vector of this plane, which is 5, 2, 1. I'm getting that from the coefficients on the x, y, and z. There's a 1 there, right? So good, I've already got that. All I need now is a point on the plane. If I can find the point, I'm done. Well, if this line, right, if that entire line is on the plane, then every point on this line is on our plane. And I just need one of them. So how can I get a point on this line? Just let t be anything you want it to be. Just get a point off this line. Let t be, let's say 0. I like 0 because it's easy to plug in. If t is 0, where are you going to be? You're going to be at the point 1, 2, 4. So surely if that point lives on this line, then and our plane contains the entire line, then that point lives on our plane. So we have a point and we have a direction vector. That's all we need. So someone else could have come in here and done this problem, and they could have said, hey, I'm going to let t be 1, and they would have a different point. Is that going to change our answer? I'll show you it's not. Okay? So let's do this. I'm going to use this point and this direction vector. So using the formula, you get 5, that's A, x minus x naught, plus b, y minus y naught, and then plus c, which is 1, and then z minus z naught equals 0. So there's a, b, c, x naught, y naught, z naught. There it is. Let's distribute through. 5x minus 5 plus 2y minus 4 plus z minus 4 equals 0. So we wind up with an answer of 5x plus 2y plus z equals, look, these are the same, but this number is going to be different, watch. -9 and then -13, bring it to the other side, +13. That is the equation of the plane that is parallel to this plane and contains the entire line. It's kind of amazing that that entire line is in there, huh? Should we check first that this point does live there? Plug in 1, 2, 4. So if I plug in 1, 2, 4, plug in 1, we get 5, 2 in here, we get 4, plug in 4 in there, we get 9 plus 4 is 13, that checks. And I said it didn't matter what point I picked, so I bet you any other point on this line is going to live there too. Should we check another one? Let's see, if I let t be 1, where are we going to be? So 1 plus 1 is 2, 2 minus 1 is 1, and then 4, ooh, if we plug in 1 here, we just get 1. So what would happen if we plug that point into this? So 2, so 5 times 2 is 10, plus 1, let's see, 1 times 2 is 2, plus z is 1. Oh, wow, it's 13? Huh, interesting. Every single point on this line lives in there, lives on that plane. That's very cool. So what if you would have come in here and you would have said, you wouldn't have done t as 0, right? And you would have been trying to come up with this equation, and you would have used 2, 1, 1 instead. So this would have changed, right? Let's see the difference. See if we get a different answer. So if I plug in here 2, plug in here 1 and 1, and distribute 5x minus 10 plus 2y minus 2 plus z minus 1, then I get, look, 5x plus 2y plus z, that's the same. Negative 10 minus 2 minus 1, that's negative 13, still 13. It works. It's the same. Amazing. We're done. Starting to get excited. I like this stuff. All right, next one. 25. Ooh, find the equation of the plane through 3 points. Find the equation of the plane through 3 points. So if someone gives you 3 points and asks you for the equation of the plane through those, can you find it? I feel like I've got something on my back. What the hell is that? It's weird. Oh, okay, I'm going to draw this. Because we have 3 points, it'll be easy for me to draw the plane. 0, 1, 1. So there's 1 point. 1, 0, 1, which is this point. And then 1, 1, 1, 1, 0, which is this point. And connect these together like this. Now imagine that triangle extended out in every direction, and what you'll have is a plane. So what's the equation of that plane? Well, here's how we're going to do this. You know what? Let me go get something else. See how long my video is. All right, this will be the last example I can do on this video. All right, so here's that plane, right? So it's those 3 points connected here. Like this. So we got the plane sitting there, right? Creates this plane. I'm trying to find the equation of this plane. So what do we need for the equation of a plane? A point in a direction, a normal vector. Well, I have 3 points to choose from, so I'm just going to use this as my plane. I could use any one of them. And then all I need now is a normal, right? What's the normal vector? Well, if we look at the vector that's going to point out of this plane, right? It's going to be perpendicular to this plane. Then what I could do to get that normal vector is I could look at creating 2 vectors on my sheet of paper. So the vector that would go from this point to this point, put an arrow on it because it's a vector. I could take this, which goes here to here. So let me label these. This is A, which was this point. B was, oh sorry, no, A was, what was A? 0. Oh shit, hold on. 0, crap, my picture's wrong. Start this over. I think my picture was wrong. 0, nowhere on the X, Y, 1, Z, 1. And then 1, don't go left to right, go up 1. And then 1, 1 out this way like this. Creates that triangle. I don't know why I screwed that up. Okay, so look, here's what I'll do. Sorry about that. Doesn't matter. I've got 3 points. I'm going to label them now. 1, 1. This is A, so that's A. B is 1, 0, 1, so this is B. And then C is this one right here. C. Okay. So if I take these 3 points in space, they make a plane. I can, again, for the equation I need a point, so I'm just going to use that first one, A. And then what I did is I came in here and I'm going to create a vector, a couple of them. A, here's B, here's C. So how about I do a vector like this? I'll stick with kind of the same as what I was doing before. From here to here, vector, and from here to here, a vector. And I'm trying to find this normal that's pointed out. So what I do is I take these two vectors, right, and I cross product them. And when I cross product these vectors, right-hand rule, right, this thing will stick out. Or it could be possibly pointing out the bottom, but it doesn't matter. This is a normal vector. And so I just need to cross those two vectors. So I'm going to try and find this normal vector. I'm going to define it to be the vector that goes from B to A crossed with the vector that goes from B to C. If I cross those, I'm guaranteed a vector that's perpendicular to both, so it's going to be perpendicular to the plane. Hope that makes sense. Again, I apologize about my crappy drawing to start. So I need to actually come up with some vectors here. So what is the vector that goes from B to A? So from B to A, so I'm going from here to here. So I'm going to take 0 and subtract 1, negative 1. I'm going to take 1 and subtract 0, so that's 1. And then I'm going to take 1 and subtract 1, which gives me 0. So that's the vector going from B to A. Now the vector from B to C, I'm going to do 1, take away 1, which is 0. I'm going to go 1, take away 0, which is 1. And I'm going to go 0 and take away 1, which is negative 1. And now I need to cross those two. So to cross those two, I'm going to write them vertically. I'll put the answer right here. So I'm going to get the I component first, so I cover it up. I go 1 times negative, so that's negative 1 minus 0, so just negative 1. And then I cover up this one. Negative 1 times negative 1 is 1. Then minus 0, so I have 1, but then I'm going to subtract it because it's the j. So minus 1. And then I cover up the k, and I get negative 1, take away 0, so just negative 1. So that's my direction. That's my normal vector for my plane. Okay, this is n. And now I just use the plane formula. I think I can squeeze it in. Well, I'll just put it right here. I need a point, which I've got. I need my direction, my normal vector. So that's your ABC. This is your x naught, y naught, z naught. So I should have negative 1, x minus 0, minus 1, y minus 1, and then minus 1 times z minus 1 again, equals 0. And then at this point, I just distribute through, get negative x minus y plus 1 minus z plus 1 equals 0. And I need all my variables on one side. I could leave them on the left, but they're all negative. So why don't I move them to the right? The left side will be 2. Then I get x plus y plus z. And that's the same as writing it the other way, x plus y plus z equals 2. And that's it. That's number 25. And that's good. Okay, I'm going to stop this video. These videos can only be about an hour long, and then it breaks it into 2 videos, so that's why I try and do just 1 hour.